Uh, our first presentation is by Dr. Marina Konstantatou. Marina is, as you will have gathered, one of our award winners from last year. And she's been working, she did her PhD in the engineering department in Cambridge and has been working on the linkage between architecture and engineering. So we'd like to hear first from Marina, please.
Good evening, everyone. So it's a pleasure to be here tonight, and I'm gonna present to you my PhD thesis, which finished last December. So unfortunately, I'm not a student anymore. So my thesis was on geometry-based structural analysis and design. And the starting point of which was graphic statics. So graphic statics was a 19th century geometrical methodology for design and analysis of two-dimensional trusses, which was very, very popular at the time. As you can see on the table on the left, you had this type of reciprocal or dual diagrams, the form and the force diagram. So you can think of the form diagram as a two-dimensional truss with some external loading, and then this would have a force diagram. So the force diagram, the lines, the length of those lines, what they denote in a very visual and intuitive way is the actual axial loading. And this is very interesting in a number of ways. First of all, you do have this very intuitive idea of the forces that go through your structure. Moreover, if you have a force diagram which has all those closed force polygons, you're sure that your structure is in static equilibrium. And moreover, more fundamentally, actually, it's more profound, is that if you see this bidirectional link, it means that you may not start with the form as an input, but you can start with the forces. So you can start designing the forces, and then the form is an output. However, as you see on the right, maybe you can observe some limitations of the method at the time, because if you wanted to do something quite complicated, you need tedious hand drawing. So if you want to change something, it would take you quite long. So there were a lot of people who contributed to graphic statics, and some of them are less known than others. My thesis focused in one particular approach, and that was the approach by Maxwell. And Maxwell, of course, is very famous for his contribution to physics, but he equally had a really profound contribution to structural analysis and design, which is not as known. Graphic statics declined through the 20th century for a number of reasons, such as the emergence of other competitive theories, but it did survive as a structural morphogenesis tool. So here we see a very nice example by Maillard, who was an eminent structural designer. So through graphic statics and through using the forces as a structural genesis drive, he was able to design those very elegant concrete bridges that use material in a very efficient way. And the more familiar example to us, this is King's College Chapel. So you see it has those very elegant, very beautiful fans, and the ceiling, in fact, is really thin. The reason for that is that back then, the architect, the engineer, and the craftsman were the same person. So the structural performance did inform the architectural form, and that resulted in material efficiency. However, today, things are quite different. So the architect, the engineer, and the craftsman are different people that often they can't easily communicate with each other because they speak very different languages. So now the structural performance is not an integral part of the early conceptual design stages. In fact, in quite a few cases, it's that the architectural form is made at the beginning, and at later stages, this is given to the engineer to make it stand, to make it work. And that can result to material inefficiency. So how do these things inform contemporary structural and architectural design and analysis, and in particular, Maxwell's approach that we just mentioned? So here is a diagram from my thesis, and what it shows is two of the basic ideas of this approach. So we don't have only one diagram. We don't have only the 2D truss diagram. We have four reciprocal interconnected diagrams. So we have the form diagram, the force diagram, and then more fundamentally, Maxwell did this very profound observation that a 2D truss in static equilibrium must be a projection of a polyhedron. That polyhedron that we see at the top on the left is a special type of the Airy stress function, which has plane faces. But this polyhedral stress function can also be reciprocated to produce a reciprocal polyhedra. So what we have now, we have a pair of reciprocal polyhedra at the top, and if we just project those down, we have a pair of form and force diagrams. So we can use those two to design and analyze our structures. However, it's not only that we can make 2D trusses in static equilibrium. Through the force density method, which was developed in Germany in the 70s, we can lift this two-dimensional truss that now the horizontal equilibrium is guaranteed. We can lift this up to a spatial grid shell or vault in static equilibrium. What is more is that with the Airy stress function, we can essentially sculpt our load path. We can ourselves define explicitly our load path. We can define through the convexity and the curvature of the Airy stress function which edges we want it to be in tension or compression. And thus, we can generalize this method not only to compression-only vaults, but also to compression and tension grid cells. One example, which was a collaboration with Skidmore, Owings, and Merrill in Chicago through my industrial secondment there a couple of years back, is to apply this method, to develop and apply this method for grid cells for big landmark projects. That's an example here is something similar to the great court roof of the British Museum. So here, those quite complicated polyhedra are a pair of reciprocal form and force polyhedra. And as you see on the right, for the form polyhedron, let's say, you can see that some of the edges are convex, some of the edges are concave. The result of this is that we can explicitly say what type of load path we want for this particular grid shell. And then with the force density method, we can lift this up to a grid shell which has only actual axial loading and no bending, which is very important if we're looking for material efficiency. However, there are also other ways that we can do that. This is a part of my academic secondment at the University of Pennsylvania. So on the left, you see some of Maxwell's diagram of his very important 1964 paper. So what he said back then was that if we see on the top left here, if we see this dimensional truss, we can see that as a projection of a polyhedron. So if we want to recreate its stress function, and in this way create its force diagram and have a visual representation of its forces, we can just lift those internal points to the third dimension. So following this construction, we thought we can generalize it one dimension up. So if you have a three-dimensional truss, then you can take some of its internal points and lift them up to the fourth dimension to make a four polytopic stress function in this case, which we can map to its reciprocal, then project down again, as we saw at the beginning, to obtain a force diagram. So by doing that, we guarantee that the design happens within equilibrium space. So the design and analysis are really interconnected. Basically, you design by analysis. And by doing that, we can make quite a rich language of, in this case, these are spatial trusses of exoskeletons for tall towers. And briefly, I'm gonna mention some cross-disciplinary applications. So the fact that the theory is very geometrical and abstract means that it can be applied to a lot of things. One example is stress fields in structural concrete. So that was a collaboration with some colleagues at ETH Zurich. So here, through the truss analogy, if you have the initial topology of the strut and tie network and the external loading on your concrete wall or slab, then you can make an initial form diagram and you can lift this up to your polyhedral Airy stress function. By doing that, you're sure through the planarity of the faces that this is compatible in the sense that you have only axial forces. At the same time, you can readily then obtain your force diagram. And what you can do next is that you can combine your form and force diagram into what we see in diagram E, which is essentially your stress field. So this is a direct way of producing stress fields, and that also gives us the detailing of the nodes, which is quite useful. The same thing can also be applied to yield lines in structural concrete. So through the well-known truss analogy, if you have a yield line pattern, by lifting it to its polyhedral area stress function, you can both check whether it's compatible, so whether it's going to collapse or not, but also this area stress function is actually a visual representation of the external work. And then if you combine the form and force diagrams, you can also have a visual representation of the internal work. So all this geometrical framework based on reciprocity between form and force diagrams and the reciprocal stress functions can give you a very, very visual and intuitive way of understanding how to design and analyze structures, and hopefully in a way that both architects and engineers can understand and communicate with each other. So that's all from me. Thank you very much.
Marina, thank you very much indeed. That was absolutely great, and a very elegant way of building a language between architects and engineers, which I'm sure is in some cases long overdue. We have time for one or two questions. Those of you in the audience, you will have seen the instructions. If you would like to put your hand up or ask a question on the Q&A, that's fine. But I'm not seeing anybody. And it takes a little time. I think most of the world is on Zoom at the moment, so we'll wait just a moment. And I'm seeing Richard L. So Richard, would you be kind enough to give us your question, please?
It looks like a powerful technique to the extent I understood it, but I wondered how you saw it being taken further. I mean, would architects now presumably wouldn't know what to do with the sort of diagrams you're producing? Are you seeing something being built into tools that they would use in the early design, or how would you take it forward?
Thank you. Yeah, so that's right. As part of my thesis, I started developing such tools because, as you say, what is important is for the designer, the user, whoever that is, the engineer or the architect, to be able to easily access those tools and be able to design and analyze with them. So one software you may be familiar with is Rhino, which is a CAD software. So it's like AutoCAD, let's say, but more contemporary, different one. So this particular software has a platform called Grasshopper where you can script your own tools, and then people can use them. So the things you saw are already existing tools within the Grasshopper platform. So I can send those to my colleagues and we can take it from there. But as we say, it's really important in terms of accessibility for those tools to exist, because if we just give the theory, it's not easy for a practitioner to start using it.
Thank you. Marina, that was absolutely superb. Thank you very much indeed.